Um,
Okay.
a very
Morning.
a very pleasant good morning to one and all. I Kishore Kumar Okede, an assistant professor at Department of Aeronautical Engineering, Harvard Institute of Engineering and Technology. I welcome you all in today's webinar. Uh, we all know that there is a huge gap between industrial practices and current academia. So to bridge this gap of aeronautical engineering students, this webinar is arranged. Uh, Fatigue and damage tolerance is an integral and inevitable part of the aerospace structural design. And as we know that all industrial practices are coming from the subjects that we study in the academics, but particularly fatigue and fracture mechanics is such a subject and area that has come from the industry to academia. And to enlighten us on this wonderful area, we have invited Dr. Kishore Brahma. So I'm very pleased to welcome Dr. Brahma. Very warm welcome to you, sir. Let me all introduce Dr. Brahma. He has an experienced aerospace expert with over 32 years of service in research and development, engineering, academia, and skill development sector. He did his graduation from MIT Madras and master's and doctorate from Indian Institute of Science, Bangalore in aeronautical engineering. His research work was focused mainly on fatigue crack propagation of metallic materials. He was awarded with Mrs. Sabita Chaudhary Memorial Medal from Indian Institute of Science, Bangalore. He was involved in high technology projects on aerospace and defense during his tenure as a scientist in National Aerospace Laboratory, Bangalore, and has received recognition as an outstanding contributor on two different occasions. As a part of professional career, he has worked in various fatigue-related projects of aircraft like LCA, LTA, various fighter aircraft, military transport aircraft, military helicopters, single-aisle, long-range, wide-body customers NAL, Ministry of Defense, ARDB, ADA, Airbus Germany, Airbus France, Pratt& Whitney USA. Currently, he is working as a head training of Bridgenow Academy, Bangalore, which is affiliated to Aerospace and Aviation Skill Sector Council under the National Skill Development of Corporation, Government of India. Once again, sir, a very warm welcome to you. I request viewers that if any question is there, kindly post it on Facebook or you can WhatsApp me. I will take it forward in the question and answer session. Dr. Brahma, sir, I hand over this session to you. Kindly go ahead.
Thank you, Kishore, for the introduction. Good morning to all of you. So it is a pleasure and a privilege to be invited by you people to share my experience on the niche area on fatigue and damage tolerance. And it is good that I should thank the Parallel University organizers to give an opportunity to give a talk to the audience. And to start with, I would like to briefly talk about the organization for which I am working, just for the sake of information to the student as well as faculty. So obviously, all of us are aware of National Skill Development Corporation, which is set up by Government of India, and they have a different skill sectors, and Aerospace and Aviation Sector Skill Council is one of them. And you can see in this slide, the skill sector has identified 72 job sectors in different areas related to aero industries, right from your airport ground activities to your other high R&D activities like aviation system engineer, structural design analysis, aerospace design quality. And out of 72 job roles, it is basically 7 to 8 job roles are meant for the people who have graduated from aerospace as well as mechanical engineering. And Our Bridge Now Academy is one of the skill training partner with NSTC, like Aerospace Aviation Skill Sector Council, and this basically provides fresh students, graduates, to make them skill industry as per the qualification pack or guidelines provided by ASAC. And the courses we do offer is related to aerospace structural design analysis, aerospace technical publication, avionics design and engineering, avionics software testing and validation. And of course, we have other activities like automotive engineering, telecom and all, airlines and all. But the services what we provide from Bridge Now Academy is for fresh graduates, for corporate, then corporate CSR obligation, government, defense establishment, university and colleges, and also recently started with consulting project management for R&D work. So basically, fresh graduate, I just mentioned about that the people who are interested to get into aero industry, they have to get into the skill of aero industry. That's what we provide. So obviously, there are certain mandatory procedure to be followed to be selected for the undergoing the. These are a paid training center, and corporate OEMs also we do for upskilling of the employees of different companies in different areas. What I mentioned in the previous slide, and also corporate CSL evaluation. Sometimes companies are supposed to provide 2% of profit to the society, and some companies they do spend their corporate society responsibility, that is CSR, towards also training. Apart from some of them might be investing in developing infrastructure, hospitals or schools and all. But in this case, the GKN Aerospace, which is a UK-based company they have in Bangalore office, last 3 years they have been sponsoring the students of financially weak students to undergo this 4 months training on aero industry things. And government defense specialists, of course, we provide that for defense people and all. University and colleges, of course, we try to have a interaction, collaboration with the university based on the skill set. It may be either introducing some syllabus, as industry-centric syllabus to be included in semester. And recently, we have been interacting with the SK, the Sri Vishwakarma Skill University in Haryana, where they have introduced the PGDM program, postgraduate diploma in aerospace structural design in collaboration with BNA, where BNA was involved is preparing the curriculum and also providing the training as per the industry practices. And it is started with 2016, our Bridge Now Academy. Till now, 900 engineers have been already trained in a different domain. And more than 80% placements are successful. And basically, the most important on demand is aerospace technical publications, because there are almost 80 plus companies in Bangalore alone. They cater for the technical publication for aero industry. And most of the time, our parent company, that Umlaut, which is earlier known as P3 company, they take the people the day they finish the courses. With this, I will start my technical things. So the agenda is like this. What is before getting to more detail about that? Basically, I will be covering the detailed aspects without going into too much detail. What are the practices involved in fatigue and dimensional analysis of aerospace structure from the OEM point of view, or manufacturer, original equipment manufacturer point of view? So first we have to start with the importance of fatigue and dimensional analysis, then goal of fatigue and dimensional analysis, then what are the regulations and means of compliance, and type of damages. As per the regulation, you have to ensure the structural integrity with respect to certain damage, what are there, and EIF, that is called equivalent initial flaw size, then classification of structures, then load spectrum, and design criteria and status factors, then fatigue and damage analysis, tolerance analysis. So before getting into analysis, we do need to know what are the inputs required, and how they are obtained, and how it is relevant to Affinity analysis. This picture shows that basically one has to do the fatigue and damage analysis for any component to arrive at this inspection. To arrive at the inspection, that is first time inspection and repeat inspection, then one needs to do crack growth curve and also to study residual strength analysis of the structure. So I will be explaining in subsequent slides, but to generate the crack growth curve or to residual strength in the presence of crack, one has to have a knowledge on elementary engineering fracture mechanics, which is relevant to stress inspector, is proportional to apex stress and square root of crack length. I presume that students will have, participants who are attending things will have basic knowledge on fatigue, SN curve, then crack provocation, and the DADN versus delta K curve, that crack growth curve. I will not go into detail of that, but how those informs are used for a fatigue and damage analysis of aerospace structures. Now coming to importance of affinity analysis, we know that there is a certain agencies in each country that they do give the airworthy of a aircraft after ensuring is and satisfactory to meet their requirement. So as you know, in USA, in the Western country, it is a Federal Aviation Administration, FAA, and their regulations is known as FAR, Federal Aviation Regulations. And for a passenger aircraft, all is relevant to Part 25, for which it says that to ensure the damage tolerance requirement of the structure, then one has to do the residual strength of the airframe structural component shall not drop below the limit load to ensure its integrity. Basically, limit load is a load which occurs once in a lifetime of the entire life of the aircraft, and it is always below the yield point, so within elastic range. And of course, residual strength is the strength of the component, which for if component is a virgin and without any flaw or crack, it will fail in the when it reaches the ultimate stress or strength. But once a crack is there, and as the crack grows due to the repeated loading, your residual strength also varies. So, but it varies in such a way that as crack grows, it also residual strength decreases. But as per the requirement, damage tolerance requirement, your residual strength should not drop below the limit load, for which limit load has been derived from static point of view for a given load spectrum for a given type of aircraft. And also to ensure that inspection must be scheduled to ensure that the required level of residual strength is maintained. So how do you ensure that the residual strength is maintained? Because it's not a small part where one can do in situ measurement. So one has to do some affinitive analysis that how the residual strength varies with crack length and all. And whole driving point for doing damage tolerance analysis is nothing but to do the crack growth propagation starting from a detectable crack length to the final crack length, to arrive at what interval one has to introduce the inspection, so that when routinely it is inspected as per the schedule, if at all there is a crack, it can be detected and the corrective action can be taken, thereby ensuring that safety of the passengers. So above requirements are made through damage tolerance analysis of individual structural components of an airframe, and thereby ensuring the structural integrity of aircraft and safety of passengers. So obviously, once one does this analysis like residual strength and getting into inspection interval, sorry, I think it will get into the thing. Okay, now what is the objective of doing the fatigue and damage tolerance analysis? As I have explained already, one has to ensure to demonstrate. So the main objective of the fatigue analysis is to demonstrate the reliability of the structure up to the design service goal or the extended service goal. So design service goal is nothing but these are parlance word used by manufacturer. The total fatigue life of the aircraft is called design service goal. And sometimes at the present scenario, it is difficult to procure a new aircraft. So once the life is coming close to its total fatigue life, they do some analysis, testing and all to extend its life. It's called extended service goal. So depending the outcome of the analysis, it can be extended. So whatever the case may be, whether it's a design service goal is known as a DST or EST, extended service goal, one has to carry out the fatigue analysis to arrive at what should be the threshold inspection thing, inspectable, and what is the critical test. So at least it is to demonstrate that if life is for 40,000 flight hours, so in that case, what to do, one has to do the fatigue analysis to see that it goes minimum of to 2 times than the design. So life means to show that it's up to 40,000 flight cycle is there. One has to demonstrate that it is 80,000, 2 times of that. And to determine the inspection threshold for multiple load paths and crack arrest fail-safe structure. There's some concept used like a single load path and multiple load paths. And they do the crack arrest test. Kishore, can you hear the noise, background noise? Is it okay? Or?
You can go ahead, sir. It's okay.
Because the neighbor house, they're doing some drilling. I told them to stop. Is it okay?
No problem. It's okay, sir.
Okay, so I will explain you in the subsequent cycle what is a single load path and multiple load path. So in those cases, one has to do this fatigue analysis to come out with what should be the inspection threshold. Similarly, the objective of damage tolerance analysis is, as I mentioned in the previous slide, one has to do the residual strength analysis. You can see that when crack length is 0, it will fail at ultimate strength. So that is ultimate strength of the material. But if crack is there, obviously your residual strength, the capability of withstanding the total length, strength will come down. You can see that the crack length will be increasing, your residual strength also will be reducing slowly. But as per the requirement, your residual strength should not drop below the limit load. So that is the one of the objective to ensure through the analysis. And also there's a multiple site damage analysis, because if you say that if crack is originating from a single location, then you have a residual strength requirement here. But once you have a multiple site requirement, means crack originate at different locations, though they are not critical at the as per se, but they will coalescence will take place at a certain point of time, where a residual strength also falls down substantially. So to take into account of those multiple site damage analysis also has to be demonstrated. Now I will just briefly describe the regulations. What are the regulations for especially for fatigue and damage tolerance? There are regulations for like static strength, vibration and all. From certification point of view, we have a 25-point FAS that the Federal Aviation Regulation 25.571, which is particularly means for fatigue and damage tolerance analysis evaluation. So plus AC is advisory circular 25.711D, which refers to damage tolerance and fatigue evaluation, including widespread fatigue damage. And these are for the sake of completeness, I'm just giving the other regulations related to only FNDT, but it is related to like ST 25.24 is the engine imbalance, then structure repair evaluation, then major operational rules are like the FR 25.1529, that is related to instruction of continued airworthiness and continuing structural integrity program for larger transport category airplanes. Then for aging aircraft, there's board federal regulation, CFR, are available for this. But what I will be focusing mostly related to damage tolerance of fatigue evaluation through Affinity analysis. So now what are the requirements from the regulation? If you see the general statement that an evaluation of the structure must show that a catastrophic failure due to fatigue, corrosion, manufacturing defect, or accidental damage will be avoided throughout the operational life of the airplane. So this is the basically requirement from the airworthiness point of view, that whoever manufactures the aircraft, what are the type of aircraft, if it's applicable under FR 25, they have to ensure, demonstrate that if at all there is damage, there should not be damage and they should not lead to the catastrophic failure, and damage may occur due to either fatigue or corrosion, manufacturing defect, or accidental damage. Okay, but they will not tell you how to achieve it, achieve this requirement, but they have to demonstrate that. So this is very general with respect to damage tolerance evaluation. So obviously you have to identify what are the probable damage locations in a structure or component, and what are the crack initiation mechanism, crack growth time history, and crack detectability. These are the requirements from the damage tolerance. This is the guidelines provided by FR 25.571. So it includes your widespread fatigue damage assessment supported by full-scale testing, identification of possible damage location, extent of damage, damage tolerance analysis and test, then determination of inspection threshold and interval, and inspection threshold for certain type of structure based on the crack growth instead of fatigue-like approach. So these are the requirements. In continuation of that, there is one more is called safe life. So we have a fail-safe. There are three design philosophies. One is a safe life, fail-safe, and damage tolerance. And fail-safe, damage tolerance, both are almost same. Then safe life, where with damage tolerance requirement, paragraph B, that's what I mentioned in the previous slide, is not required if the applicant establishes that their application for particular structure is impractical. So in today's scenario, all components of aircraft structures are damage tolerant except the landing gear, which is only they go by safe life, because that's very critical and important component. So they will not do the damage. Damage tolerant means structure is tolerant to damage. That means the structure can function and operate in the presence of a crack. But in landing gear, it's not expected to have any crack or damage. So that's why it is a safe life evaluation. Even earlier also, before tailplane, attachment of tailplane to the fuselage, they were used to be safe life because they are fixed at the time of manufacturing. There never used to be accessibility. Now this design has changed, so even attachment of tailplane to the fuselage, also they have to demonstrate the damage tolerance. Okay, so under this, these are the requirements from the defendant point of view. Now, as I mentioned earlier, your regulatory authority, they will never tell how to ensure or comply the regulation. We have seen the previous two slides, A, B, C. You have to demonstrate to the regulator before your aircraft is get certificate for the airworthy. So from means of compliance is left to the designer and manufacturer how to ensure that. So obviously, means of compliance, like these are the acceptable means of compliance one can demonstrate. Like if you want to have to demonstrate that your fatigue life is able to meet your design service goal, it will have an adequate fatigue strength. Okay. So these are they have to choose a material which allows adequate fatigue, because they cannot have say on the type of load, because it is expected to see during the flight, but they can definitely choose a particular material which has got very good superior fatigue strength. As you might have seen earlier, initially it was started with 7075, which is very good for static point of view. When it is realized that it's not good for fatigue point of view, they moved into 2024. That is aluminum, copper, magnesium alloy material, which is very good in fatigue. Later on, the people tried using aluminum lithium alloy, which is a 10% increase in static strength and a very good performance, also 10% less in density, but they are very bad in fatigue point of view. The especially thick metal of aluminum lithium alloy. but the thick plate one is used for your cross beam and load frame from static point of view. Now, obviously, people are going for a composite because they're very good in static strength. So another aspect one manufacturer can think of is design precautions and proper material choices. So there are certain, basically the crack will initiate due to the point of stress razor or concentration. So you have to use the best practices in static design against failure. Then again, this consideration of multiple site damage. So obviously, we have seen that one of the requirements that structure has to be evaluated from multiple site damage, which occurs at the fag end of its life, because it has got exposure to the not only the mechanical loading and also corrosive environment and precision cycles. So obviously, crack will start at different because there are thousands of rivets in the fuselage, and the crack will initiate any point of that. But they are so small, it's not critical. But even some areas start having small crack, at one point of time they will join together, and your static strength will decrease to zero. Then also another way of ensuring the integrity of things, adequate inspection program. Okay, so that's why you have to do the crack growth analysis, and you find that what is the detectable crack, from detectable crack length to critical crack length, how many number of cycles or flight cycles take. In between, one has to at what interval one can introduce the inspection so that the crack can be detected. Especially threshold crack detectable depends on the configuration of the structure, geometry, locations, lightning and all, and also depends on the type of non-destructive equipment is used. If it is a particular location, ultrasonic is used, your detectable crack length is 8 mm. So you cannot use ultrasonic in the place where crack length is less than 8 mm. So unless it's 8 mm, but chances are that 8 mm ultrasonic inspection technique may fail to detect, because again, it's a specific operator technician's objective. Okay, so what happens then? If you have a next inspection interval, definitely that will be detected, because the next inspection will occur much before another two inspections. So it's not so critical. So obviously it will able to detect, and corrective actions can be taken. So usually how the manufacturer comply those acceptable compliances, generally philosophy is to comply with the regulation requirement with the analysis supported by test. And both are closely linked and cannot be addressed separately. You cannot do the only analysis alone or test alone, but obviously number of tests can be reduced by choosing similarity of the structure and correlating for a given test result. The number of tests can be reduced, but the analysis can actually be done. Because of the large number of areas to be considered in the fatigue and downstream evaluation, a high degree of reliance is placed in analysis. So now we saw the importance of Affinity analysis and how a test must be performed to ensure that Affinity analysis methods result in conservative values. Then now we'll get into what are actually one has to consider the damages and their source, which is resulting in the structural integrity, or which is responsible for damages leading to the crack propagation. So if you recollect the FR 25.7 general statement, you can see the statement is underlined: fatigue, corrosion, manufacturing defects, and axillary damage. Okay, so these are the culprit or source of damages which may occur. So obviously during the analysis, one has to consider what are the damages that may occur due to fatigue and corrosion, manufacturing defects, and accidental damage, so that the appropriate analysis can be done properly. So this few slides will be explaining on the type of damages and what are their sources. So one is the local fatigue damage, which a single fatigue damage can be expected locally where the stress is high compared to the neighboring element. So obviously in aircraft structure there are a lot of holes, fasteners and all. They are the major source of crack initiation. Kishore, is it okay or sound is too much?
It's okay, sir. You can go ahead.
Because I informed my neighbor, she said that she will do it, but I don't know.
No problem, sir.
Go ahead, I'll send to some other room.
It's okay, sir. You can go ahead.
Sorry, I'm apologizing. I told him otherwise I need to again remind him.
No problem, sir. Go ahead.
Okay, so your local fatigue damage that may occur due to inheritance, no? You know the fatigue occurs due to the repeated loading. So obviously, once structure is experienced by repeated loading, there will be damage that will be induced, and that will lead to the crack initiation. And obviously, there is a widespread fatigue damage. That is a set of similar geometrical elements stressed at the same level are likely to be fatigue damage at the same time. It's known as multiple element damage. Actually, widespread fatigue damage is a very generic term, and there are sub topics. One called multiple element damage, and another called multiple site damage. This is an example of multiple. You have a skin with a stringer or a load frame. So they might be equally loaded, not exactly same loading, but it will be within 5% if they are equal loaded. So crack may initiate from one of the things, may not be the sequentially, but alternate thing, but still then one has to take care of that. And another is under the same area, it can have a multiple site damage. So in that case, in the same single row itself, you have a crack initiating at a different locations. You can see there may be not critical, very small, but they started at different site locations. So one has to take care of this analysis to ensure the structural integrity of the aircraft. And obviously, corrosion fatigue occurs due to the climatic exposure, environmental exposure, nothing to do with the loading and all. And it is based on the calendar. And also, this is taken care of by providing corrosion protection paint and all these things. So, but still then one would expect that corrosion may occur in due course of time. Then manufacturing defect. Basically, the defect is called a deviation from design specification during production resulting in a product defect, frailty or shortcoming. So this is what happened based on the experience of the one particular aircraft. Is F111, is the US Air Force in 1969. This particular aircraft is designed for 11G. It can withstand 11 times of its own weight acceleration due to gravity, and it is both subsonic and supersonic. To achieve both the operations, the wings are pivoted. You know, at subsonic, at the landing and takeoff, one would prefer to have a subsonic for which wing has to be in flat rectangular mode. But once it goes to the high altitude and to have a supersonic speed, then it has to be delta type. So both the wings can sweat backward. So it used to be pivoted through a pivot pin. Unfortunately, there was a defect, manifest defect, which could not be detected after the production, but that led to failure at 4G level when it was freezing, and hardly it has covered only 100 flight cycles. We supposed 100 cycles. It's supposed to go for 1600 flight cycles. That would have taken 10 to 12 years. So that's what happened to manufacturing defect. That's why your regulatory authority says even you have to ensure that catastrophic failure will not occur if at all there is a manufacturing defect. Then there are different reasons for manufacturing defect. It is due to either inadequate fastener joints, worn out tools, poor material batch, and generally if you want to do some chemical milling, if you have not done proper mass protection, that will also may lead to manufacturing defect. Now, obviously, accidental damage. So, it is basically the physical deterioration of the structure caused by discrete events. So those are the source of damage is foreign to the aircraft, which may be due to the ground handling equipment, cargo handling equipment, aircraft maintenance, aircraft operation, and runway debris. And sometimes weather effects like hail and lightning strike. So that may induce the actual damage happen accidentally. But still then one has to do the analysis considering the probability of having actual damage also. So the type of calculations required, if you see the overview for fatigue damage, so these are as per the regulatory, the damages one has to consider the fatigue damage, manufacturing defect, actual damage, and corrosion damage. Obviously, for fatigue damage, one has to do the crack growth calculation as well as crack propagation. But manufacturing defect, we don't have any option on that. As soon as one has to do the crack propagation thing, even though there may not be crack propagation, but during the analysis, one has to assume that there is a initial crack length. That we'll see that is called equivalent initial flaw size. With that, one has to do the crack propagation calculation. Even accidental damage, there is no fatigue calculation required, but for crack propagation calculation. But in corrosion damage, there's no calculation involved because there's nothing to do with loading. There's a question of environmental exposure, so that has to be taken care of by providing the proper corrosion, anti-corrosion paint and sealant and all. Now, I was coming back to equivalent initial flaw size. So, you know, to do the crack propagation analysis, one has to assume some crack. Otherwise, fracture mechanics cannot be used. So, to start with, to give the background, how this equivalent initial flaw size is there, that in fatigue analysis performed, it is assumed that the standard and nominal quality is met. That is, all manufacturing procedures are followed and meets the quality control process using whatever the process is evolved for that particular product. However, some manufacturing defects will be present on aircraft as it's not possible to have an exhaustive manufacturing control. So it occurs inadvertently. And defect might pass through manufacturing and quality control phases in spite of all precautions. So obviously during the damage level evaluation, based on fracture mechanics calculation, must consider manufacturing defects. There are, and crack propagation curve requires at the initial crack propagation length. Because if you are using fracture mechanics, we have to assume a initial crack length. Since corrosion, feeds, clamping, gloss, etc. are not physical cracks, it is necessary to define an equivalent initial crack. So this is the basis on which one has to come out with equivalent initial flaw size. Okay. Very interestingly, is how these initial damage assumptions were made based on again earlier very exhaustive tear down of a lead aircraft, which has already come to the end of its life. They stripped open all the primary structure, secondary structure, and wherever the crack is expected, they did some investigation using scanning electron microscope and all. Then they found that especially in holes and all, there is a tool marking will be there in the beginning, because it's possible by using sophisticated technique like electron transmission one, and also by counting the number of strains that is induced due to the repeated load, can go do the backward calculation to exactly come out what is the initial crack length and how many number of flight cycle has also done through that. So based on that, they found that majority of the parts and holes and all, this can be have a 0.005 inch size, 0.127 mm. And also they found that generally this is called quality flaw. They also thought of having a row flaw, which may occur in the process, which will be 10 times of the quality flaw. That is one. If it is quality flaw is 0.127, the row flow will be 1.27 mm. So there are two types of equivalent initial flow size are considered. One is called manufacturing quality flaw to represent initial damage size in secondary structure, and also the rogue manufacturing flaw RF to represent initial damage size in primary. That I will explain in subsequent slide. So based on that standardization, you have a two types of thing. You have a single load path where major load passes through a single load path. For if you have a hold or cutout or other areas, depending on the thickness of the structure or component, one can assume what is the initial crack length. Okay, this is all standard one can use, and this is required to assume to do any crack propagation calculation. So similarly, for multiple load path, where load can be transferred to one end to other end through multiple load paths, again based on the thickness, there are different size of initial flaw sizes are assumed. So this is the basis for to do your damage tolerance analysis. So this is what example of a stringer and skin combination. So as a part of the procedure, one has to assume both the quality flaw and as well as the rogue flaw to start with. Even though there may not be flaw, but as a part of procedure, one has to if you are assuming that skin is a primary structure and stringer is secondary, then you have to use primary damage in the skin, then secondary damage, that is a quality flaw in the stringer. Or one can do assume that primary damage in the stringer, then quality flaw or damage in the skin. So there are two scenarios. I mean, there is possible for the stringer skin combination, and one has to do such assumptions for crack propagation as a part of damage tolerance evaluation or analysis to evaluate its capability. Now I will get back to the classification structure, because this is also part of a requirement that because you have a entire aircraft consists of thousands of components, elements. So on what basis that which component has to be analyzed for Affinity or not. So that's the classification is based on some categorization. So before taking up the structure, you want to see whether, as I mentioned in the just a few minutes back, all structural components of aircraft fall into two categories. Either it has to be safe life or damage tolerance. And as of now, I mentioned here, except landing gear, all are done for damage tolerance evaluation. So if it is, if your structure is not damage tolerant, then one has to go for the safe life, where you have to do some testing and find out what is the number of cycles, then use a scatter factor 4. Then that will be the limiting life of that structure. You can see for this example here, if you take a component, assuming that from crack initiation to critical crack is taking 1 lakh cycles, and if you use the scatter factor 4, then the life will become 25,000. So obviously, from safe life evaluation, that means as name suggests, safe life. Life is very safe. So once it reaches 25,000 cycles, though it's you can see from this graph here, it's far away from the crack initiation. Forget about the failure, but still once it reaches 25,000, you will have to withdraw or replace the thing. But in damage tolerance, you have to do the crack propagation analysis, generate a curve, and find out at what crack length it can be detected using what type of technique you are using, and what crack length is failed under the given spectrum loading. Then within this interval, you insert equal repeat inspection. So even though initially, if technician misses the crack length or the detectable crack length, say 8 mm, if you are using EC eddy current, then detectable crack length is 4 mm. And if you are using the roto, is a high frequency or low frequency, then it can go up to 2 mm. But the chances are that even if you miss 2 mm, but your critical crack length may be 30 mm or something like that. So first time if you miss a detectable crack length, second in the inspection interval, definitely it will be detected and corrective action can be taken. So these are the 4 categories, A, B, C, D. These are basically the definition, and in subsequent slides it gives the example. I'll just go through just like that. But for this slide, you can see the generally aircraft structures are categorized A, B, C, and C. A is a structure identified as the principal structure element, PSC, and B is structure which failure or determined could compromise continued safe life or landing by an adverse effect of category A structure. Then structure failure is detachment will not compromise continuous safe life or landing, but where the potentially large size of release element need to be considered. And these which are not any of ABC. So based on that, the conclusion is the normal adaptable configuration is any structure which is identified A and B, they have to be undergo fatigue and damage tolerance analysis. C, there is no damage tolerance analysis required, only fatigue. And D is not required at all. So I'll just quickly go through that. This is a flow chart how to arrive at a complete structure based on the logic analysis. You can categorize A, B, C, and D. And you, as I mentioned, A and B is called significant structure. So basically the structure which carries your inertial load, aerodynamic load, and pressurization is called PSC, principal structural element. And if there is a additional requirement of inspection required, then it becomes significant structural element. Okay, SSE. So usually A and B, they will be done for affinity analysis, and C only fatigue analysis has been done, and this is nothing required. So this is basically the flow chart to this arrive out category AB. So this is a definition. As I mentioned, your ground pressure load, their failure result in catastrophic failure is called category A. So these are the examples for CLS. Then again, category A that is identified in wings and empennage. Then your engine mounts is basically start and thrust links, pitch and air reaction force fitting, landing gear and thereafter reunion, and main stuff, inner and outer parts. So it's not talking about the landing gear components. Okay, that is safe life. Then category B, where it says that are not considered to be category A, but whose failure or detachment could adversely affect a PSC, that is principal structure element, and so compromise continues. So what are the examples? So landing gear doors, inboard flap track pairing attachments, funnel from belly pairing. Now these are few examples of category B. And category C, obviously, which are not SSC, neither A or nor B. And obviously, failure or separation of these elements has no consequence of the continued airworthiness of the aircraft. And this is just done from the economic reason point of view. So, like an example is winglets. So, if something happens to winglets, your aircraft is not going to fail catastrophically. So that's why it is called only. But the fatigue test will be done to ensure that its life of whatever 40,000 flies is met. But no crack growth analysis is required. Now, that is one set of categorization structure we saw. That another categorization is called based on the redistribution load in case of failure. Obviously, there are two cases, single load path and multiple load path. So, in multiple load path, we are providing some additional redundant structure so that in case some element fails, the neighboring element also will take care of the load till it is detected during the scheduled inspection. For an example of a single load path and multiple load path, if you think of log and fork attachment, if you have one log and one set of fork, is a single load path, because if log is connected through a single load path, load from one end to another load will go through pin. But if there is failure of either one of the forks or log, obviously that is a catastrophic failure. But same log, if you have provide two logs and three forks, obviously one of them is fails, nothing is going to happen. But it can be detected during the regular inspection schedule. But it is designed, that's the example of multiple load path. Even your skin stringer, you have so many rivets. Your stringer may fail, but skin has to catastrophic failure to occur, the entire skin has to grow to in more than 1 meter length or so till a catastrophic failure occurs. So these are the examples of single load path and multiple load path. Because that is relevant how to arrive at the inspection interval. For example, for single load path, we know that you have to do the crack growth analysis, right? To assume from a certain crack length, as per the standardized we saw, either 0.005 inch or 0.127 or 1.27 m, depending on whether you are considered quality flow or raw flow. If you start growing it, obviously at one point of time it will become detectable, then it still continue, and at one end it will have a critical crack size where so this much inspection interval available where you can introduce the inspection interval in between so that you can easily inspect it. But the structures are very complex in geometry. So multiple load paths were externally inspectable. This is a combination of stringer and skin. If stringer fails, then crack will grow from the skin. So one can only see from outside. Okay, so you have a two path. First, the stringer failure is occurred, but it can be accessed because it is inside. So crack will initiate here, like in the skin. But once it becomes detectable, see. So now your inspection interval is available only this much. Okay, so similarly, you have another multiple load path structure where inspectable after failure of one load path. So this example of two logs and two forks here. So one of the log failed, but we will not able to detect it because it is inside that. But if a failure occurs, the neighboring log can take the load. But if you imagine the scenario, this log has failure, but other log you can able to see at the time of other logs, so that we have a wider growth period available to arrive at the inspection interval. Then inspectable before, so here another case, we have a stringer, teeth type of stringer with skin and all. So with the reeve things, where you can see the crack can grow from the stringer and but unfortunately it cannot be detected from inside. Again, once it comes outside only, you can detect on the skin. Then only we can see that. So, but here one can see that compared to the previous stringer and combination, where is the jet type of thing, but here a T. So there are two locations here. One is the crack growth failure of these things happening, stringer. Then you can grow that. Now, obviously, you need to know what is the critical locations, because there are thousands of locations will be there. How to arrive at the critical locations. So these are basically the guidelines where we can look for the critical location, review of joint areas, review of elements in tension and shear where static margin, where reserve factor is low, then where the high stress comes. So these are the different guidelines available to select the SSE, structural segment element. Now, obviously, to do the analysis, you need a load as the input. So how do you arrive the load? So basically, load spectrum is statistical difference of history of load of stresses. So history are usually obtained from previous measured experimental or flight data and converted into exceedance diagram. So basically, exceedance diagram is number of exceeds at a predefined value versus number of flights per hour. So you can say typical exceedance curve for Falstaff for the fighter aircraft, then combat aircraft, and this is LCA, light combat aircraft. So, and it basically is used to represent the exceedance curve because it is easy to generate the spectrum. So there are three methods of how to generate the spectrum from exceedance curve. This is one of the examples where you can start from one point to the other end. Like that, you keep on generating spectrum till all peaks and troughs are adjusted. So because they provide the basis for the most fatigue and crack progression analysis. So one has to consider the different type of loads. One is the ground loads and another is called fatigue loads. So loads are basically taxi, takeoff, and ground landing, braking, ground operations, and obviously fatigue loads are all exhaust So this is a typical one flight cycle, right from going from one place to other, like your Bangalore to Chennai. If you go, one flight cycle is right from taxi to takeoff, then ascending, climbing, then experience some gust and pressure. In the meantime, the pressurization also will occur. So this is a light, and to generate the spectrum, one has to know what are the type of missions it undergoes in one flight. So this is one idea schematically shown right from takeoff to cruise and landing. Typical passenger aircraft, how it happens, and they are divided into different. But this shown as example, there are 30 missions has been identified. So depending on the which level it is, so one can then, because the type of load is experienced by the structures is different, so we need to find out what are the different missions. Obviously, based on the mission, one has to do consider the internal load based on the what are the external loads. So we have seen the external loads are two main categories. One is a flight load and ground load, and another is called basically supervisory load with incremental load. So this is the typical inertial load, aerodynamic loads will be there, and the incremental loads consist of your example as a gust during the flight. It doesn't occur continuously. Once in a while, it happens. So generally, the internal loads are generated based on 1G condition airborne, which is vertical gust, lateral gust, vertical maneuver, lateral rolling maneuver, and on the ground we have rotation, landing impact. So these are being considered and converted into internal loads using FEM. Okay, so for the particular component, you have a FEM model available, and based on this loads, one has to consider what are the stresses by that particular thing. Obviously, you know the aircraft also experiences thermal cyclic thermal loads. So one has to consider things, because during the flight at ground level in the airport, it will be seeing the environmental things, but during high altitude, it will be seeing a different temperature. And also from one place to other place, one can also experience a type of thing like a polar case, tropical place, different areas. The structure material we experience in different type of temperature. So one happens the thermal cycle. And also system equipment also have a significant heat effect on the surrounding structure. So one has to consider the thermal mission also. Like the flight mission also has to be considered. How do you arrive at the thermal mission? See, this is a typical one flight from taxiing, takeoff to the landing, coming down. This is the case, and you can see the schematically what are the temperature in degree centigrade varies. At high altitude, obviously temperature is low, and it may go beyond between -40 degrees depending on what altitude in the area. And also during landing, the temperature will also rise. And to arrive at the mission mix of the temperature, one has to consider this is the typical how temperature varies in atmosphere as per the international standard atmosphere. So we have a different region like tropical, Arctic, and polar condition. So this is extracted based on the departure and arrival of the aircraft at a different location. And you can have a cross mission where defined as a mission that combines different kinds of environmental route that it may go through different regions. For an example, an aircraft may take off in tropical environment, cruise at international standard atmosphere, and land in a polar condition. Then it is called cross mission. So one has to consider, because your thermal cycle will affect on the static life. So generally, this is a typical thermal mission mix stress. This is having 4 missions, like short logistic, long logistic, practical, and training. So, and these are the environmental conditions, your standard atmospheric things, and tropical and polar. So these are the combination, and the worst combination is taken as for the analysis. So basically, we'll have 2 types of thermal effects. One is called global thermal stress, induced mainly by combining large structural components made of different materials and spread through whole structure or etc. Another is local thermal stress in joints of dissimilar, like your composite with aluminum alloy metal, obviously their thermal coefficients are different. So once they go through exposed to the environmental conditions, then it will have a different effect. So one has to consider the stresses arises due to that. So this is a typical flowchart how to arrive at whether if you are selected one material for affinity analysis, whether you one has to consider a global FEM based or local based thermal analysis. So if a similar material assembled, if no, I mean you have a composite, and then you have to take care of a global as well as local thermal analysis. And if it is similar measure, then you have to see whether it is affected by thermal stresses or not. If yes, then you have to consider global thermal analysis. If no, then no thermal analysis required. Now I will come to the design criteria. So basically what happens, once you design aircraft, it has to meet certain design objective in terms of life or thing. In aircraft structure, I mean, especially in aircraft, one has to consider that what is the design criteria. So during the analysis, one consider what is the design aim and what is the calculator, your analysis test value you are getting it. Then you have to show that on scatter factor. Obviously, scatter factor is used to take care of the uncertainties in terms of loading, testing, environment, batch effect of the material and all. So and calculated by structure can be like as a NF for the fatigue life, and NP is a number of cycles for conservation. So basically, during the analysis, if you get a value, then you see that by taking into account the factor whether it is able to meet the design aim or not. To example, so design elements for aims for the aircraft thing is your design service goal, that is for total fatigue life, and inspection threshold, at what fast inspection will be taken place, and at what interval you will have a inspection interval. So this is a typical example of short, medium haul, medium long haul. Say your design service goal is 40,000 cycles, flight cycles. So that may still will take 30 to 40 years, and your threshold will be taken the 20,000, and subsequent thing will be done at 7,500. So next will be 27,000 is the first is there. The next inspection will be the till it is 8,000 flight cycle. So obviously you have plenty of inspection interval to do that. So the inspection interval is, as I mentioned, is a two types. One is called threshold, the first inspection that can be done at the detectable crack length, and another is called the repeat inspection interval. Assuming that the aircraft is entered into service at a certain T is equal to 0, your total aircraft is designated design service goal, your inspection threshold will be occurring at the first inspection. It should not be less than it should not be more than the half of the total life. If 30,000 is a cycle, so design service goal, your inspection threshold should not be more than 15,000 flying hours. It is less than or equal to that. Then later on, minimum 2 to 3 inspection interval has to be provided. Then only you are entering, even the aircraft is flying in operation, in service with a crack, but there is no danger to the integrity of the structure, because failure will take place when it reaches a critical crack length. But before that, you have already scheduled the inspection based on the analysis, and during that, corrective action can be taken. So I will just quickly go through this scatter factor for certification. This is what different types require, like durability, nothing about the fatigue, then widespread fatigue damage, residual fatigue strength, and large damage capability, and which this shows about what is the purpose, applicability, and what approach has to be done to achieve the durability, and what is the scatter factor. That means during analysis for a fatigue of a component for a given spectrum, you have to demonstrate that the aircraft life is 30,000. Life as assuming the 30,000 flight cycle. In your analysis, you have to demonstrate that it is 5 times of 30,000. So like means 1,50,000. No, it will qualify your fatigue life. Then only it will be certified. And if you are doing with a test, then instead of scatter factor, instead of 5, it will become a 3. Because you are able to simulate with the properly with spectrum and all. So that's why scatter factor reduced. Similarly, for widespread fatigue damage, you have to demonstrate your scatter factor should be more than the DL LiDAR. So like that, this is the scatter factor for life, and this is scatter factor for inspection in threshold and inspection interval. So for all structure category A and B, you have to do the for single load or multiple load part, you have to demonstrate that you are 5 times of threshold. So this also, if you are doing this, again 3 times. So these are the factor standard factors is being used by the manufacturer. Then finally, I will come to the end, close to that. Finally, how to do the Affinity analysis. I have covered the previous slides. What are the inputs required? In this subsequent slides, I will just put streamlined and process I have mentioned it for the ease of understanding. Here for Affinity analysis, this is the typical flowchart. What you need is the input data. Then need to find selection critical response. Then material and geometry data for each structural significant element. Load path analysis. Then fatigue and load stress spectrum for each SSE. Then fatigue and crack propagation calculation. Then load path analysis. Then finally, apply your design criteria. So I think I have all covered the previous slide thing, so that quickly you can. So there is nothing much in detail about that. So basically, your input step 1 is nothing but your information gathering involving your expected what is the design service goal estimate, and what is the threshold for initial inspection, and what is the repeat inspection. So you during analysis you have to demonstrate that, and what are the fatigue missions that is required for the load generation. So you typically you'll have a different fatigue mission for type of the aircraft, and general fatigue load is like cabin pressure, flight, ground loads, all the details are required as the input. In step 2, we need to have a identify a structural significant element. So this is again is already known from the handbook and all. What is the principal structural element? What is the secondary critical secondary element and all. So where principal PSC, which is failure of that element, will lead to the catastrophic failure of the entire aircraft. So that particular component you consider, you have to see whether it is in which category, like ABC. Then material geometry data, obviously we need local geometry, sizes, thickness, because particular aircraft growth thing. So material affinity is nothing but we need to SN curve for that particular material with stress concentration, stress ratio, then also preferably for the environmental condition, and also the fracture toughness values. So these are the parameters which you have studied in fracture mechanics or in the crack propagation course. So step 4 is fatigue load spectrum for each structural signal element. So there is a procedure available that I already described, not much in detail, but this is what you do the time load time history you will get. Then use FEM analysis to convert external load to the internal load. Then generate the spectrum from the exceedance curve. Then you do the rain flow counting technique to arrive at the precisely what cycle, what peak and trough constitute a cycle. Your step 5 is fatigue and crack propagation calculation for each structural. See, this is a typical example done for a particular attachment. You can see that we have assumed quality flow of 0.127 mm. If you see that as crack with flight number of flights, the crack grows here. But you can see the critical crack length is coming around 9 mm. If you do the only crack growth analysis alone. But if you should do the residual strength of that material when crack is 0, we'll have close to 400 plus. That's the ultimate strength of the material. But as crack grows, your residual strength also decreases. But as per the regulatory authorities, the regulation certification, your residual strength should not fall below the limit load. So this is a lower limit load which is derived from the static analysis. So if you see that, that corresponds to your 5 mm. For if you take the critical crack length supposed to be 9 mm, but due to the regulatory authorities, the airworthiness it's 5 mm. So you can see your 5 mm to, and here this much only available for your inspection interval, not from the 5 mm to 9 mm. Okay, no, not sorry, from 0.1 to 7 mm2, or even detectable crack length, if you see, it is around 2.3 or something like that. It's not from 2.3 to 9 mm. It is from 2.3 to 5 mm. The cost within that, you have to arrive inspection. But you can see the below the number of cycles is exceeding the life of the aircraft itself. So it doesn't call for any inspection interval. But this is the example. How the this is all done based on the fracture mechanics point of view. And step 6 is load path analysis, because I mentioned this is essential to know whether the particular element or component or structure is multiple load path or single load path. That will decide what interval is available to check in or arrive at inspection interval. Then final is analysis. You see whether it meets the design criteria based on whether it's a single load path or multiple load path. If it exceeds the requirement, then you can do the optimization. Otherwise, you have to make again changes in geometry and all. So to finally conclude my presentation, the takeaway is that you have seen the familiarization the main regulatory requirements for Affinity evaluation, and also both evaluation means you do it through analysis, then type of damages and their sources, and the need of equivalent initial flow size and what are the standard sizes available for types of single load path structure or multiple load path. Then classification structure based on categorization and load path like A, B, C. Again, load path is single load or multiple load path. Then we have I just touched upon overview of gender fatigue load sector, because it's very extensive detailed analysis required. Obviously, nobody generally shares the load spectral generation because it's a proprietary. But that is a very generic, basic way one can ultimately one has to do a FEM to generate a load spectrum from the experience curve. Now, experience curves are for standard type of aircraft available in and design criteria and scatter effect classification. So the step-by-step process involved in carrying out fatigue and damage tolerance analysis of a structure. So this is a typically procedure followed by OEM, and details are given for each aspect how to get into that information. So with that, I think I'm concluding presentation. I have taken, I think, 10 minutes more than this.
Thank you so much, sir. Thank you for such an enlightening and informative session. Now, I would request viewers, if you have any question, please post it. Meanwhile, we have one question here. Sir, what are the current NDT methods that airlines prefer to find out the initial damage length?
Come again, I didn't get your question. What is that?
What are the current NDT methods which airlines prefer to find out the initial crack length?
No, this is all standard, right from your basic from red eye penetrant, not basic. Basic is also called naked eye. Naked eye, red eye penetrant, then you go into move into ultrasonic, then radiography. Radiography, not much. Then your eddy current. Eddy current also there are two varieties. Is the high frequency and low frequency eddy current depending on the, and also the thing laser matrix stereography. Those are very advanced thing that is being used by U.S. Air Force. But if you talk about civil airlines, this is the restricted. This is the NDT technique.
Okay. Sir, what is the criteria that we take into consideration when preloading is given while assembly is done for the fatigue?
Actually, that is a beneficial effect. And with my experience with working with Airbus, particularly for last 10 years, my experience is I think it's applicable to all the manufacturers also. They go by conservative way of doing it. So having preload or having some compressive process, not technology process where we can induce the compressive residual stress they don't consider those aspects. Assuming that it's not non-existent and do the calculation the usual way. With that calculation, if it clears the objective, then nothing to worry. Now, for example, another example to give you the understanding. You know the crack growth curve, dA by dN versus delta K, which starts from your threshold to the final critical, no? Is region A, region B, region C, or region 1, 2, 3. Your threshold and the combination of stress and the flaw size, if it is less than threshold value, crack will not initiate. And the crack growth equation also available, Corman's modified equations, which takes care of not only your threshold, K1C, and also stress ratio effect. But in OEM, they don't consider threshold aspect in the crack growth equation containing crack growth threshold. That, of course, they don't use Paris equation, because in Paris equation, they don't, they modified Paris equation used by the Foreman, where it takes care of your K1C and stress ratio. So they go by conservative things. So all beneficial effect they don't consider.
Okay. So thank you, sir. Thank you so much for giving us this wonderful opportunity to hear you and to know the nuances of this wonderful field of fatigue and damage tolerance. So I'm very much grateful to you, sir, that you have found some time for us from your busy schedule. And we look forward to have your cooperation with the Parul University hereafter as well. Thank you, sir.
Sure,
Thank
no
you so
problem.
much for giving the
Thanks. Thank you.
Yes.
I'm signing
Yes.
off then. Okay.
Okay, sir. We conclude here.